Thank you, Sean. Thank you, everyone. Thank you for inviting me. So today I'll be talking about this work that I've been working on with some people in Brian's group. And this is a joint collaboration. This is the crew. So Brian is my advisor, and then Greg and Xiaokai are postdocs at Brandeis. Charles is now a postdoc at Caltech, and Jonathan Harper is a postdoc at Yokohama Institute in Japan. So I'll be talking about how to holographically describe a measurement on the boundary theory. And in particular, we'll see that no problem. In particular, we'll see that in some specific setups, this measurement leads to teleport the bulk information from some boundary subregion to some different boundary subregion. So the talk will be divided in 3 parts. I'll give an introduction with the main motivation and main results. And then in the second part, I will focus on a calculation, which is a purely bulk calculation in a specific ADS3 CFT2 setup. And then I'll give some intuition of how this teleportation actually happens using tensor network models of holography. I will mostly focus on the third part on stabilizers code, essentially the HEP code. In the paper, there is also a section about random tensor networks, which I'd be happy to discuss after the talk. I have only a summary of the results of that because I won't have time to go into that in detail. So let's start with the first part. This is my canonical one-slide review of a DSCFT, where we know that quantum gravity in a asymptotically ADS spacetime in d+1 dimensions is dual to some boundary conformal-free theory, conformal-free theory living on the boundary of this spacetime. And one very important feature of holography is that holography can be interpreted in terms of a quantum error correcting code. In this sense, the bulk degrees of freedom can be seen as the logical qubits, and the boundary degrees of freedom can be seen as the physical qubits of this code, and the spacetime can be represented as a tensor network defining this code. Now, holography has taught us a lot of interesting things. One of the most interesting things that holography tells us is that spacetime is an emergent feature. It emerges from the quantum entanglement of the boundary theory. And there is a very nice, precise way to quantify this, which is the Ryota-Gainaki prescription to compute the entanglement entropy of a boundary region. So if you consider a CFT on the boundary and you want to compute the entanglement entropy of some subregion B, then what you can do is consider the bulk dual spacetime and consider the extremal surface homologous to this region B, calculate the area of this extremal surface, and then divide by 4G, and that will give you the entanglement entropy of this region B. Now, this is clearly a way to see how the entanglement in the boundary theory leads to a geometric description, and there is a geometric dual of this entanglement. And that is useful. Also, of course, there are correction to RT. There is HRT, and there is quantum extremal surface prescription. But for the purposes of this talk, RT would be enough for what we will be talking about. And then the tensor network models give a very nice representation of this duality between entanglement and geometry, because the entanglement of the boundary theory is essentially graphically represented by these tensor networks. And this geometrical structure of the tensor network can be interpreted as a spacetime. Now, one important feature here, just a quick review of ADS-CFT, is also that if you have a subregion B, you can in principle reconstruct all the information within the entanglement wedge of this subregion B. I will use entanglement wedge a little bit improper. Yes, please.
Yeah, this is not a criticism of anything you said. Everything you said here is what's usually said. I would just like to point out that the third part, that for me we can reconstruct everything in the entanglement wedge, really implies the rest. I mean, we already knew decades ago, long before ADS-CFT, right, that if you have a subregion of space, that there's entanglement across the boundary of that region that diverges proportionally to the area.
Right.
By some cutoff. And you could just take, once you know that B is dual to the entanglement wedge of B, right? It's clear that that entanglement has to be mapped to the boundary. It
Right.
has to have a boundary counterpart, right? And so it's just one of the many things that gets mapped to the boundary.
Yeah.
From that boundary point has nothing to do with how space-time emerges. It was always part of how the structure of space-time, and it's just one more thing that had to be correctly mapped to the boundary, the duality. So I think this case of space-time emerging from entanglement has been a little bit overstated due to the historical fact that we didn't first understand what Ryu-Tucker and Nagi meant. I think it meets this third thing.
Right. But in this sense, you can say that, yeah, okay, you have just a duality between a boundary region and a bulk region. And then
it has to take care of the entanglement, like it has to take care of any particle that's sitting there and anything else.
Right.
That's just part of the
right.
part of the deal.
Yeah, but it is true in some sense that the entanglement structure determines where the entanglement wedge is located, essentially, because the entanglement structure of the boundary theory determines the trajectory, essentially, of the RT surface, since the RT surface is what computes the entanglement entropy of this boundary region.
But a lot of things determine that trajectory, right? It's also what matter I put in the bulk.
Oh, right,
that forms the space-time.
Yeah.
Or the entanglement between matter. It's treated on exactly the same footing as the vacuum entanglement.
Yeah.
So I don't think there's anything special about the vacuum entanglement anymore. I think that was a bit of an overstated case.
Okay.
I mean, it's just true that the structure of space-time involves a lot of entanglement, but we kind of knew that before HEP-QIS. Sorry, I'll stop
Okay.
right there. Anything wrong? It's a sort of way of presenting the story which is abundant in our field and which I think is maybe time for rethinking that.
Okay. Yeah, thanks. And yeah, anyway, for the purpose of this talk, the idea is that the entanglement wedge can be reconstructed for, the important part is that the entanglement wedge can be reconstructed for this boundary region B. I will be a little bit sketchy on this, in the sense I won't be super precise in what I mean by entanglement wedge, because I will indicate with entanglement wedge this region comprised between the boundary region and the RT surface in one fixed time slice, which is of course not the right definition of entanglement wedge, because the right definition would be the domain independence of that region. But for the purpose of this talk, we will mostly be talking about a fixed time slice, so I will refer for simplicity to that subregion as an entanglement wedge. And so one question one could ask, and this is the main question that we asked when we started working on this, is suppose that you measure, or in general you manipulate the entanglement structure of this boundary theory somehow, then how does that translate into some manipulation of the bulk theory? So in order to ask this question, we know that one way to manipulate the entanglement structure of a theory is by performing some projective measurement on the theory. And so suppose that we have control over a boundary theory. For example, if it's in the continuum case, we will have a CFT, or we can have the external leg of a tensor network. Then suppose that we project, and I will make that a little bit more precise later, but we make some projective measurement on subregion A. Now, this subregion in principle can access everything in the entanglement wedge, and so once you project and you measure that subregion, you can extract information in the entanglement wedge, which will not be part of the bulk description anymore. But in order to extract information which is deep into the entanglement wedge, you must perform some very correlated measurement, some non-local operation on the boundary. If you want to see it from the quantum error correction point of view, the idea is that you must measure a logical operator of the bulk, which is pushed to the boundary to a very, very non-local and correlated operator. So one could ask, well, what if I perform a simple form of measurement? And I will make precise what I mean for simple. Essentially, the idea is try to measure something much more locally without measuring some very non-local operator or highly entangled operator on the boundary. Then what does happen in that case? Is it the case that the bulk is still completely erased, all of the entanglement wedge, or maybe some pieces of it is conserved in the bulk description? So how much bulk can you really erase when you make this measurement? In this talk, I will focus on the opposite limit of this highly entangled measure. So essentially in this super local as possible measurement in the boundary, and I will explain that precisely what I mean by that. And let me mention that a very important fact is that I will frequently be talking about measurement, but what we really mean is post-selection, because it's very important to know what's the outcome of this measurement when we perform it. So from an operative point of view, you can see that as performing the measurement many times until you obtain, in many copies of the system, until you obtain the desired outcome. So knowing what the outcome of the measurement is important in this story. Okay, so I will focus in this local projective measurement on some subregion A of the boundary. In a tensor network, this is pretty naturally defined in the sense that you just take the external legs in your subregion A here, and you project them independently on some product basis. And so you obtain just a local measurement on each leg. Now in the CFT, this is much more complicated to define. Intuitively, it's a very UV operation, because what you do is essentially taking this idea of measuring each external leg and then taking a continual limit. So you're essentially trying to measure each point of the CFT in subregion A on some specific state, which is clearly something not very clear to define. The intuition here is that if you have a lattice, a CFT discretized on some lattice, then you are projecting each side of the lattice on a product state of the sides. Sorry, you're projecting these sides in subregion A on a product state, so each side of the lattice independently. Now, clearly, this yields a state after measurement on region A, which has zero spatial entanglement. Now, there is an interesting fact that we will use, which Masamichi Miyagi and Takayanagi and collaborators showed that a class of state that has zero spatial entanglement are boundary states or Cardy states, which are the states that are used to define to describe boundary conformality theories. So the idea that we will use here, and this idea was originally introduced actually in a paper by Takayanagi, I think even before that by Rajapur in a microscopic setting, and then Takayanagi used it in holographic setups, is that in order to define the post-measurement state of this CFT, you can consider a Euclidean path integral that prepares the state at this time reflection symmetric slice. And, I think this is, OK. This time reflection symmetric slice. And then, since region A is in a boundary state, what you do is inserting a slit around this region A and then imposing conformal boundary conditions around it. And that is equivalent to having the region A projected onto a boundary state.
Don't you want it to be a specific boundary state so that you basically destroy, I mean, like one that corresponds to like a zero tension grain that just sits on the former RT surface of A?
That's a good question. Exactly what's the dual of this specific, I will describe that in more detail later, but what is the exact dual of this setup is much more complicated to define because this state is obviously singular because you are projecting on a product state between region A and the rest of the CFT, but it's, you can use conformal maps to regularize this setup and then build a holographic dual. Yes, in principle, what you want here is a specific boundary state with some specific boundary entropy, and that will determine the tension of your brain, which is not necessarily zero. Like you can consider any kind of tension and then study what's going on, and that's what we'll do.
I see. I would have thought naively that the outcome of this process should be that you basically just erase the entanglement wedge of A and you're left with entanglement wedge of AC with some.
That's exactly the point. Like in principle, you could do that if you consider, say, a zero tension brain. But if you consider different tension brains, and so you're post-selecting on some boundary state which does not have zero boundary entropy, but maybe has a large boundary entropy, you actually retain in the entanglement wedge of AC more than what you expect, and that's what we call Boole teleportation. But I'll make that much more precise in a second.
But this particular example where you just project onto a product state of all the legs. Are you saying that even in that setting, you can end up with a state on AC that includes some of the former entanglement wedge base?
Yeah, that's the idea. The idea is that if you project, if everything that you're doing is projecting on a boundary state, if you project on a boundary state which does not have zero boundary entropy, but has a different, like a positive large boundary entropy, for example, you can retain more than, you don't erase all of the entanglement wedge away, you erase less. Well, in this paper, they showed that in general, boundary states have zero boundary entropy. So projecting on this boundary state, as long as the boundary state that you pick is a boundary state with non-zero boundary entropy, you can do that. Now, there is an interesting question there, which is operatively how you project this state on some specific boundary state, and that's an open question.
I'm asking just a very specific question. When you project onto the state you just described, which is a product state of all the legs, what is the boundary entropy that results from that?
Yeah. I think that depending on the measurement basis that you choose, still the same product state. The idea is that depending on the measurement basis that you choose, even if it's always a product basis, you can obtain different boundary states with different boundary entropies.
Doesn't say that I projected on the product state of the individual legs?
Yeah, you project on some product state, but the product state can be, for example, if it's a bunch of spins, you can be all spin ups, or it can be some product state which is open boundary conditions, and that leads to different boundary states. So like,
it has an effect on the boundary entropy.
It has an effect on the boundary entropy, because the post-measurement state is some boundary state that has zero or non-zero boundary entropy, depending on the measurement basis that you pick.
If there's a zero boundary entropy, you lose everything, right?
You lose, yeah, essentially you lose, if it's zero boundary entropy, you lose intuitively the entanglement wedge. It's not super clear to see that it's exactly all the entanglement wedge. I'll explain that a little bit more later, but yeah, if it's zero.
You are not really measuring everything. So
you're not measuring the information deep into the bulk, yeah. And so
Two different things, right? You said that it depends on the basis, but then you also at some point said it depends on which particular product state I project on.
Right.
Those are not the same statement.
Those are not exactly the same statement.
Because the basis is already, we're done with the basis. You've told us product states. Those form a basis.
Well,
so the basis is completely specified by what you just
well, you can have different product bases. For example, you can measure, what I mean is you can measure, for example, say that you have two qubits that you're measuring, you can measure sigma z, or you can measure sigma z and sigma x on the two. And they're two different, so you project onto different eigenstates, right?
There's a basis. When you said you product state of external legs, I was assuming that you've already, it's one state per leg. You're not grouping the legs back together.
Yeah, that's right. But you can have.
That completely specifies the basis.
But
it doesn't specify the state, but it specifies the basis.
Yeah, okay. What the mean is that you can, sorry.
I mean, if the basis is spanned by 0 and 1 for each leg.
He's saying you can post like either on zeros or like the pluses.
Yeah. You can use the plus basis, so you measure sigma x, or you measure sigma z. Those are two different bases, but they're both product bases. That does have an effect, and in principle also measuring on different, post-selecting on different states in the same basis can have an effect on boundary entropy. So the idea is just that you're projecting on a product state of the basis, and that post-measurement state will be a boundary state. Now, which specific basis in this CFT idea corresponds to which specific boundary state is a very good question that we don't have an answer to. Okay, so let me just, I'm sure we all know it, but just to get all on the same page about notation, a very quick review about what quantum teleportation is. So suppose that Alice has some state psi of a qubit that we'll call Qi and wants to send this state to Bob. Then what she can do, if she shares an EPR pair with Bob, so suppose that there are two other qubits, QA and QB, one of these qubits is in possessed of Alice, and the other one is for Bob, and they are in an entangled state, so in an EPR pair. Now, what Alice can do to transfer this state psi of qubit Qi is to perform a measurement in a Bell basis, and this is whatever is going on within this green box, and I will explain in a second why I represented it this way. And then she can send the result of the measurement to Bob with a classical communication, and the state of Bob's qubit is the original psi state up to a unitary, which depends only on the outcome of the measurement. Now, a probably trivial fact, but it is very important here, is that measuring a product state, like it is at the beginning here for Alice's two qubits, a product state onto a Bell state, so onto an entangled state, is equivalent to having an entangled state of these 2 qubits, which is what Alice is doing here, entangling her 2 qubits, and then projecting them separately on a product state. So this fact that projecting a product state onto an entangled state is equivalent to doing the opposite thing is important for what we do, because what we will have, for example, intuitively in a tensor network, is having entangled legs and projecting them on a product state. But this, since these 2 operations are equivalent, can be interpreted as teleporting the information, can still teleport the information to the remaining legs of the tensor network. And this will become more clear when we see tensor networks, but I just wanted to point out that this is true. Now, before going to the specific setups that we have, the main result is that we saw that this local projective measurement clearly doesn't extract all the information deep into the entanglement wedge because it's a local measurement. But then one can ask how much of the, if so, how much of the entanglement wedge of A is preserved in the post-measurement bulk, which will clearly be dual to only the measured part, the unmeasured part AC, so the complementary region. So we have 2 possibilities. And there is a very nice, sharp way to ask the question, which is what we will do in the bulk. So suppose that we have a CFT on a circle, and that we measured subregion A, which is disconnected, and composed of 2 segments diametrically opposed on the circle. So these segments A1 and A2. Now, if you perform this measurement, in one case, this red part is erased, so it's not part of the bulk after measurement. In one case, you disconnect the entanglement. Oh, let me mention one important fact. If this region A is larger than half of the CFT, the entanglement wedge before measurement of A is connected and contains the center. Now, after you project, the entanglement wedge of B union C, this entanglement wedge can be either disconnected and not contain the bulk information, the center, or it could be connected. These are only cartoons. It's not any specific trajectory, but could be connected and contain the center of the bulk. Now, in this second case, clearly what's happening is that whatever part of the bulk was encoded in A before the measurement is now, at least part of it, encoded in the complementary region AC, this region B union C, after the measurement. And so we interpret this, when this happens, as bulk teleportation in the sense that the information contained in region A before the measurement, the bulk information, is now accessible from a complement. Mm-hmm.
This might just be a terminology thing, but on getting operators that are deep inside the bulk, you were saying that, at least from the happy code picture, right, these are just like the logical operators, and they're going to be more complicated.
Sorry, can you repeat the question?
Oh, like on an earlier slide when you're talking about getting information deep in the bulk, like we think about it as being more complicated because it's like these higher weight operators,
right?
The logical operators.
Yeah.
But doesn't this LPM include those, or is it a difference between the happy code and CFTs?
It's a little bit different in the sense that I agree that if you take one logical operator on one logical qubit and you push it to the boundary, then that's a product basis. But it's also true that if you want to measure a whole region, so you want to push a bunch of different logical operators in haptic, there is actually a very sharp puzzle about this thing that I'd be happy to discuss later. I don't think I have time to go through that here. But if you want to project a subregion of the happy code and so push all the logical operators on multiple qubits to the boundary, then you will obtain, yes, technically still a local measurement on the boundary, but the logical operators overall will commute, but there is no local commutativity, meaning that if you can measure one logical operator, then another one, or invert them, and that's the same. But if you measure, but you cannot invert on a single leg the gates because they do not commute. So it's like you have some kind of classical correlation on the boundary measurement in the happy code in that case. So it's a little bit complicated, and especially if you want to project all the bulk qubits on a product state, which is what we'll see that this is what is relevant for this situation, then probably you actually need some kind of entangled basis on the boundary.
The starting perfect question was that in the happy code, local bulk operators even keep in the bulk or not to start?
Yeah, exactly. Like, some operator acting on a bulk qubit, its boundary, its reconstruction on the boundary will also be some polystring, which, if we're basically projecting on
But if you want to measure more qubits, then the Pauli strings don't commute, essentially. OK, so in this situation, this is a nice way to ask this question. So measure a region which is more than half of the CFT. If you keep a connected bulk, then teleportation is happening. And then we'll see in tensor networks how really this is teleportation. So let me go to our specific ADS3 CFT2 setup. So what we do is considering a Euclidean CFT, in principle, a CFT in a vacuum state, and then making this projection. Now, if you want to do that, the prescription that we mentioned before is to consider this Euclidean path integral for the CFT, and at time reflection symmetric slice, you want to insert slits along the regions that you measure. The regions that you measure, which are these two disconnected regions that we saw before.
Sorry.
Mm-hmm.
Before you get into details, when you say that afterwards the EMC can reconstruct this, very large region, are they able to do this? But they need to know the measurement outcome on A, right?
If you want to reconstruct, yes. So
what was supposed to let it on?
sorry?
They need to know which state was supposed to let it on.
Yeah. Yeah, if you want to reconstruct, yes. But you can still imagine there is a even if you don't know how, and that will be a little bit more clear in the tensor network story, but even if you don't know exactly what state you post selected on, you can still imagine that there is a bool description. And then you can decode what's going on only if you have the outcome. But yeah, I think the right way to think about it is that, yeah, they need to know the outcome of the measurement. They need to know what state you're post selecting on. OK, so we have this Euclidean path integral preparing the state on this slice, and we impose conformal boundary conditions around the slits. So this is the Euclidean path integral boundary conformal theory, a BCFT. Now, to make contact with what I mentioned before, the idea is that this slice, this lambda 2 equals 0 slice, that is where the post-measurement state is defined, if the bulk slice dual to this boundary slice is connected and you're measuring more than half of the CFT, then bulk teleportation is happening. OK, so how do we build the dual of a BCFT? Probably most of you know this. There was a proposal by Tagayanagi originally, and then Fujita, Tagayanagi, and Tonni that studied how to build a bulk dual of a conformal field theory on a manifold with a boundary. The proposal goes as follows. Suppose that you have some CFT defined on the manifold with a boundary. That here is this manifold M. It's a closed disk in this specific example. And then you have the holographic dual spacetime, which is a D+1 dimensional spacetime cut off by a dynamical boundary. And this dynamical boundary can essentially be seen as the extension of the boundary conformal field theory into the bulk. And this dynamical boundary, the simplest way to describe it is a constant tension end of the word brane, which is, for all practical purposes, a Napier surface living in the bulk with Neumann boundary conditions imposed on it, and some parameter t that determines its trajectory. Now, the tension of this brane, which is the parameter that determines its trajectory, depends on a parameter in the boundary conformal field theory, which is called boundary entropy. And that's a property of the specific Cardy state of the boundary conformal field theory. So the idea here is that if you project on some given boundary state, that corresponds to having a brane with some specific some specific tension in the bulk. So in our analysis, which is just a bulk analysis, we will just treat T, the tension, as a free parameter. And then we interpret that in terms of the dual theory as projecting on some specific boundary state. Also, I call Cardy state boundary states, they're the same thing. OK. So how do you do this? To build a dual of that setup, we have these infinitesimally small slits, which clearly are some kind of singular setup. I won't go into all the singularity problem of this setup, which is very technical and a little bit subtle. If anyone wants to discuss about it, I'd be happy to after the talk. But the idea is that we need a more regular setup to build the dual of this BCFT. And one way you can do that is by using the fact that conformal symmetry in 2 dimensions is very powerful. You can map this cylinder with slits into a finite cylinder. what this map is doing is essentially opening up this slit and mapping it to this circle. This is a cylinder. The minus pi and pi, tau equals pi and minus pi are identified. And one slit is opened up and mapped to this circle, and this slit is opened up and mapped to that circle. Now, the tau coordinate is periodic. The s coordinate has a finite range, and this parameter h only depends on the size of the region A that we measure. Now, once you have this setup, if you want to study the holographic dual, this is much simpler. This can be reinterpreted as a CFT on an interval at finite temperature, and the dual of that is known, and is given either by the BTZ black hole or by thermal ADS3 spacetime cut off by Andor brains. So what we will do is essentially, instead of building directly the holographic dual of this setup, we map it to an equivalent different setup, build the holographic dual of that, and then ask the question that we are interested in that regularized setting. And the question we're interested in, I just remind you, is this slice connected or not? And you can map this slice to a slice in the corresponding dual geometries. OK, so what are these two spacetimes? They have these two metrics. The upper signs are for BTZ, the lower signs are thermal ADS3, and the B parameter is just a parameter that depends on the map and your system. And it will be different for BTZ and thermal, but it's uniquely determined. Mm-hmm.
I'm sorry, but I lost track what you're projecting. What are you projecting on at this point? Because we no longer have a tensor network, so now we're really dealing with real CFT.
Yeah, here we're just using the prescription that I mentioned before, that if you make this superlocal measurement in the CFT, you can map that is equivalent to having a boundary state on region A. Yeah, that is a way to see it, and we use this prescription with the slits to build the holographic dual of that. But clearly, the microscopic picture of how this measurement is performed, you can see it as a product measurement on a site, discretization on a lattice of the CFT. But in the continuum, clearly, it's not very clear how to do that, and that's why we then study tensor networks to check our results in holography. So this is just a prescription for what the post-measurement state looks like if you perform a measurement of that kind.
And the reason that you're saying this opens up into these splits, A1 and A2, is like I should think of the bride, the cat sitting there?
In this setup, yes, you just have a cat prepared here and a bra prepared there, but then you can just take the whole Euclidean manifold and map it to this different manifold.
Yeah, so I'm looking, once I identify the bra and the cat, isn't that like a thermal circle?
In this case? Well, the idea is that you're just taking the whole Euclidean manifold, mapping to a different one, building up the Euclidean dual of that, and then you can look just at, you can ask some questions this way, which is, for example, whether the bulk slice, this bulk slice is connected or not, and this bulk slice is mapped to some specific slice in those spacetimes that you build to all of this different setup.
So I'm not, when those were slits, I could imagine like choosing some state, some bra and cat, same bra and same cat, of course.
Yeah.
That sit on these
Uh-huh.
on these openings. But once I've identified them, isn't that like summing over all?
The A1, A2 aren't being identified. It's only the top and bottom.
Oh,
Yeah.
You're identifying that way around.
Yeah. Sorry.
Yeah.
Sorry, I didn't understand the question.
No, it was very clear. Yeah.
OK, so we're building the dual of this now. And this is BTZ or thermal ADS3. These two metrics both define a torus cut off by end-of-the-world brains. In the BTZ phase, the tau direction is contractible. And also, this naming BTZ thermal ADS3 is somehow arbitrary in the sense that we're calling tau the Euclidean time direction, but we could have done the opposite choice here because tau is not really the time direction in our original CFT. But anyway, here we have this BTZ phase where the tau direction is contractible, and this thermal ADS3 phase where the time direction is non-contractible. Now, we know that we must have, according to the ADS BCFT proposal, two brains anchoring at x equals 0 and x equals minus h, which were the two boundaries here of the CFTR. Now, in the BTC case, this corresponds to having two separate end-on-the-wall branes. Here I'm depicting positive tension, but in principle could be zero or negative tension. While in the thermal phase, you have a connected end-on-the-wall brane going from x equals 0 to x equals minus h. If you want to make the connection to the cylinder with slits,
yeah, I do. So before you did this conformal transformation, you had some fixed cutoff, right? That was supposed to represent the discretization of the CFT.
right?
What does the conformal transformation do to that?
Right. The point is that we are not looking specifically at how to make the measurement. We are just assuming that the post-measurement, we're working under the assumption that the post-measurement state is given by some boundary state on this region, say. And so we just have this Euclidean path integral for a boundary conformal theory. At that point, you can just make the map and look at the questions that you're interested in without caring too much about how those cutoff are transformed.
Cutoff can be viewed as implemented only on A1 and A2. You don't care anyway.
I'm worried about that.
Right.
Say at the edges of A1 and A2, some of the conformal transformation might diverge.
Yeah, because this
If you ultimately formulate the class of states you're interested in on the right, then that will correspond to a very peculiar class of states from the viewpoint of the original geometry.
yeah.
In particular, you might be manipulating sort of arbitrarily short wavelength
That's
modes near the top.
right. That is exactly that old singularity problem that I was talking about that I wasn't going to mention because there is a lot to say about that. And I'd be happy to discuss it later. But roughly the idea is that yes, in this state, if you actually slice open on this slice, you have the state of the CFT is singular at the endpoints of the slit. You have a divergence in the stress energy tensor. Intuitively, the reason is that you are trying to project a state of a quantum field theory on a product state of two subregions. So when you take the cutoff to 0 and the continuum limit, clearly that becomes divergence.
So this choice is well adapted to the task of completely disentangling the vacuum in the CFT.
Right, which clearly you can do. And so there is different ways if you want to take a physical way to regularize that, there are ways that you could regularize this, which is not what we did in the paper, but the way is, well, there are at least two, let's say. One is you perform some amount of Euclidean evolution before slicing open the path integral, and so these two slits become 4 slits, or with the whole CFT, or you make the slits of a finite height by evolving with the Hamiltonian of the remaining part of the CFT for some amount of Euclidean time evolution with a proper boundary conditions. So if you really want to well-define everything and maybe study Lorentzian evolution after slicing over the path integral, that's what you have to do. But what we did, since we just want to ask a question about this connectivity, we can just use this map where you have a divergence in the map and acts essentially as a regularization of the setup and allows you to build a holography dual where you can ask whether this slice is connected or not, since that's essentially the only thing we're interested in for now. Okay, so we were here. We have these two spacetimes, BTZ or thermal ADS3. And let me just mention very quickly that you can compute the trajectories of this brane explicitly in ADS3. It's no problem. You can just find an explicit analytical solution for them. Now, you have two phases, meaning that you must have some phase transition. How do you study this phase transition? You compute the on-shell action, including terms for the brane, terms for the bulk, corner terms, counter terms, everything you need. And then you find a phase diagram, because the least action between these two phases will be the dominant one and the one that is dominant in the Euclidean path integral. Now, I will unpack this for you. This is the phase diagram that you get, where HC is the critical value of this parameter H that we saw before, the length of the cylinder, which depends only on the size of the measured region, and the parameter H. And this HC only depends on the value of the tension. You see here RT, R is the ADS radius, and RT is between -1 and 1. So this means that varying the tension, you can tune across this phase transition. Let's see a second how. So this is a plot of just the parameter H as a function of the size of the measured region. So if you measured a small region, H is large. If you measure a large region, H is small. So this means that if you fix a tension, so you project on some given boundary state and you fix the tension of the brane, then a large region, if you measure a large region, you are in the thermally DS3 phase, but if you measure a small region, you are in the BTC phase. On the other hand, if you instead fix the size of the measured region, whatever you want, and then change the tension, so changing essentially the outcome of this measurement, if the tension is large, you will be in the BTC phase. If the tension is small, you'll be in the thermally DS3 phase. Now, in particular, and this is what we're specifically interested in for Bull teleportation, for any fixed value of A, even if you measure a very, very large region, the BTC phase can always be made dominant by increasing the tension close to criticality, meaning that you are projecting on some specific boundary state with large boundary entropy. Now, why is this important? Because we saw that we want to see the connectivity of this lambda 2 equals 0 slice, which is mapped in by our conformal map to the tau equals 0 plus minus pi slice of these spacetimes. So you can ask the same question about the connectivity in these spacetimes that we built. And in particular, this is how the two slices look like. In the BTC phase, these regions B and C are the ones left after measurement, and they're connected by connected spacetime. While in the thermal DS3 phase, this slice is clearly disconnected, and in one case you have region B bounded by an end-of-door brane, and region C bounded by an end-of-door brane. Now, this means that if the BTC phase is dominant, so you have a connected slice, and the measured region is larger than half of the CFT, Bull teleportation is happening. And we just saw that as long as the boundary entropy of the state you project on, so the tension of the brane, is large enough, it's always possible to be in the BTC phase, even for a very, very large measured region A. And so this means that from this Bull point of view, Bull teleportation is clearly happening because you're measuring this very large region and teleporting the bulk information in the complementary region AC. Now, why this is exactly quantum teleportation will become very clear in tensor networks. But from a Bull point of view, this is the guess that you could have. Let me mention very quickly the boundary point of view. So when you perform this measurement, you see this phase transition between BTC and thermal DS3. So what does that correspond to in the boundary? That's an entangling, disentangling phase transition on the boundary. And you can see that by computing the entanglement entropy of one of those two remaining regions, so region B. You can do that using the artist surface in these slices that we just saw. I have a plot of the artist surfaces as a backup slide if anyone is interested in seeing how they look like. But roughly, the idea is that in the BTC phase, you have a non-vanishing entanglement entropy with an extensive piece depending on the size of the measured region, and an intensive piece, which is clearly boundary entropy. And the other case is in the thermal DS3 phase, you just have 0 because essentially in this slice, the RT surface for B is just the empty set. So this means that this measurement that we're performing, what it's doing is if you measure a very, very large region, and of course not tuning the tension to be large, you are disentangling the remaining two regions. Or if you measure a very small region, you're not disentangling them. So it seems like something reasonable, and even more reasonable if you consider that the phase transition for 0 tension happens exactly at when you measure half of the CFT, which is something that one could intuitively expect. Let me also mention that this result reproduces nicely a BCFT result in the same setup. Just in BCFT, Rajapur calculated the entanglement entropy of this region B using a replica trick. And he studied two limits, so the very, very small measured region limit and the very large measured region limit. And in both cases, up to a 1/n effect that we cannot capture in this thermal DS3 phase because we don't have bulk fields, we obtain the exact same result. Mm-hmm.
When you're saying that you have a bulk teleportation, you're considering like qubits in the bulk that aren't going from one point to another? Or
no, what I mean is that if you have a boundary theory and some subregion of the boundary encodes some bulk information, and you measure that in an appropriate state, then the bulk information that was encoded in the boundary theory is now encoded in the complementary region. And so you're teleporting the bulk information from one subregion of the boundary to a different subregion of the boundary.
Yeah, but you're not changing the bulk like itself, or?
No, you're not changing the bulk. Well, performing the measurement, you're essentially creating this end-of-the-world brains in the bulk. So you're changing the bulk description. You don't have the whole bulk. You have some part of the bulk with end-of-the-world brains, but you're not destroying all the entanglement wedge of the measured region that you are measuring. You're just taking that and parts of that entanglement wedge and teleporting the information into the remaining subregions. Okay, so this is the holographic story and the bulk calculation. Now, tensor networks allows us to see a little bit better how this bulk teleportation actually happens. So I'll start with the simplest possible model of holography in tensor networks, if you can call it so, which is a single 513 perfect code. Yep.
Before we get going on the
Yep.
So I think one way that I think you're allowing us to think about this, right, is that you could have a disconnected or a connected wedge, and maybe initially you have some region that have two intervals that have a disconnected connected entanglement wedge. Now you perform a measurement on these complementary two intervals.
Mm-hmm.
And effectively what that does, right, is it sort of ends the space-time on the quantum extremal surface corresponding to the connected entanglement wedge. So that doesn't contribute to the area, it doesn't contribute to the area term when you evaluate, normally, you'd receive a large contribution to the generalized entropy from the area term of the connected entanglement wedge.
Mm-hmm.
But that's sort of replaced by an end-of-the-world brain, so now there's no more area term, so that enormously favors now the connected entanglement wedge for these two networks.
Right.
Right. Is that a fair summary?
I think that's right. Yeah, I think that's right. Essentially, the entanglement wedge of those two regions is just trivial after the measurement because you have zero spatial entanglement. You just don't have any space-time dual to the post-measurement, to the measured regions.
Thinking about that is that prior to that, you had to sort of map or you had to have an isometry that includes the mixed state of whatever's near the boundary of the entanglement wedge and move it to the actual ADS boundary.
Mm-hmm.
And once that entanglement has been destroyed and there's an end-of-the-world brain there instead, then you don't have to do that anymore. So it's much easier to have a large entanglement wedge.
Right.
But I'm confused what happens in the case where the teleportation fails. Is it just that? So then they're still disconnected, right?
Yeah.
And that happens when the interval on which you measure gets too large.
It's too large, yeah. So it means that
there's just not enough entanglement resources in the CFT to perform the teleportation?
That's a very good question. Actually, I'll talk about entanglement resources later. In principle, if you perform the right measurement, in holography, you always have enough entanglement resource to perform teleportation, which is in fact what we find, because if you measured on a boundary state with much boundary entropy, with a large amount of boundary entropy, you can measure the region as large as you want and keep a connected bulk.
Right, because it's a field theory. There's no cutoff. I mean,
Yeah, and I think there is a little, maybe a slightly different interpretation, which is in the bulk, you have an effective theory with some cutoff, which scales, let's say, as n to the 0, and on the boundary, you have a large n theory in this semi-classical holography point of view. And
yeah, I'm sorry, I think I understand. When you say that one interval is larger than the other, you've already imposed a cutoff, otherwise it doesn't make any sense to say this. So I think, yeah, but you can then tweak that.
yeah, what I'm saying is just that the boundary theory in holography is a large n theory and the bulk theory is not. Yeah. So the amount of information that you want to teleport is order n to the 0. And the amount of entanglement resource, which is given by essentially Ryutaka-Yanagi formula before measurement, is scales as n squared. And so you can always teleport as much as you want. The point is, if you must perform a post-selection on the right state. Otherwise, it doesn't work. Otherwise, you're essentially erasing the information of the bulk.
Right. I mean, this is similar to saying like most projections will leave B and C unentangled, but there exist some projections that will leave them entangled.
Yeah,
Okay.
that's right. Okay, about quantum error correcting codes, I was saying that I'm very improperly calling this tensor network model of holography in the sense that you have one bulk logical qubits encoded in 5 boundary qubits, which are these 5 legs. And clearly, the information of these bulk qubits is encoded in the entanglement structure of the state of the 5 external legs. Now, an interesting fact is that if you have 3 external legs, you can reconstruct the bulk qubit. So the bulk qubit is supported on any 3 legs, but only 2 boundary legs cannot reconstruct the bulk qubit. In particular, if you have 3 qubits, you can measure a logical operator, which can be made to have support only on 3 legs, and extract the bulk information. For example, this is one representation of logical operators of this code, where you have sigma z, sigma x, sigma z on 3 legs, and you do nothing on the other 3, and you are able to measure x, and this is to measure z, the logical z, and you can do that just on 3 legs. But on 2 legs, that's not possible. Now, in this code, it's very nice because you can see, of course, it's not a good model of holography, but you can see exactly how this teleportation happens. There is a more formal treatment that I won't go here into, but here I just give an example of how this can happen, and it's pretty simply interpreted in terms of bulk teleportation, in terms of quantum teleportation. So suppose that you start with a bulk state, which is an arbitrary superposition of logical 0 and logical 1, and then you perform a projective measurement on 3 of the physical qubits, so the external legs. Then, depending on which measurement basis you pick, there are 2 possibilities. One possibility is that you're measuring a logical operator. So, for example, YZY, which is logical Z. And in that case, your measurement is extracting the information in the bulk. And so the remaining 2 legs don't have any information about the state you started from. In particular, they will be in some stabilizer state after the measurement, which doesn't depend on psi. The other possibility is that you measure some other operator, which is not a logical operator. For example, sigma z, sigma z, sigma z is not a logical operator of this code. If you do that, the bulk information is still encoded in the remaining 2 legs of this tensor network, or this single tensor, we should say. And in particular, how is it encoded? Up to an entangling unitary on these 2 legs, it's just a product state of 0 and the initial logical state. So, of course, if you want to decode the bulk qubit, you must know what the outcome of the measurement was. But still, you can interpret this as having the logical information stored in the entanglement of the 2 remaining legs. So this is clearly quantum teleportation, because what we're doing is taking an entangled state of these legs and projecting them on a product state, which is the second way of looking at teleportation that we saw before. And this can be made very, very precise for this 513 code. Now, so this is an example of bulk teleportation. I'm calling here tension 0 and critical. Of course, these are the only 2 possible tensions here, in the sense that either you teleport or you don't teleport the only bulk qubit that you have. Now, if we want to make something a little bit closer to holography, we can build a HEP code. Of course, HEP code is not perfect, but it's a good starting point, and it's numerically pretty nicely treatable. So the HEP code is defined by concatenating all these tensors. So you can encode k bulk qubits into n boundary legs. And to do that, you take all these tensors, the 513 tensors associated with the 513 code, and you can contract legs by projecting them on an EPR pair. Now, this model reproduces a lot of nice features, at least in some cases reproduces, for example, the RT prescription. And so it can be seen as maybe a rudimentary model of holography. So what we will do here is take some subregion A, perform a projective measurement of the external legs, and then study whether the bulk qubits are still reconstructable in the remaining subregion. To do that, what we do is study the mutual information between each bulk qubit and the remaining boundary. So you can do this numerically pretty easily. And we see that we can essentially tune the tension by choosing the measurement basis, just like it happens in the 513 code. And if you want to tune the tension by performing some measurement, what you can do is search over basis, measurement basis, and try to minimize or maximize this mutual information between bulk qubits and boundary after the measurement. So if you maximize the mutual information, this means that you are keeping the bulk qubits, and so you have a near critical tension brane. If you minimize it, it means that you are erasing the bulk qubits, and so you have a zero tension or something like a zero tension. So these are numerical results. When you see yellow, it's large mutual information. Blue is small mutual information. So essentially, the bulk is erased whenever it's blue, and the bulk is kept whenever it's yellow. Now, these are two different setups. In one case, we measured one subregion, and in another case, we measured a disconnected subregion like we did in holography. And you see that if you maximize this mutual information, you seem to get something like a critical tension brane. If you minimize it, it seems like you can just disconnect the two remaining bulk regions. So, and on average, it looks like the zero tension case is more likely. This is an average over measurement basis. Now, this seems very nice, but it's actually, there is a problem with this picture. From here, it seems like everything can be reproduced, but this is not the case, because these end-of-the-world branes, in some sense, are not well defined, in the sense that when you erase these qubits, for example, this qubit here in the center, you're not really completely erasing it, because there is still residual mutual information between that qubit and other bulk qubits. So that doesn't have any mutual information with the boundary, but it does with other bulk qubits, which clearly doesn't have a very nice interpretation in holography. It would seem like you have some mixed state in the bulk entangled with something which is not part of the bulk description. And in fact, that's a finite n effect, in the sense that if you had all these bulk qubits to be a few and a lot of boundary qubits, you would expect the entanglement to only be between bulk and boundary and not among different bulk qubits. And so when you erase that entanglement, you erase it also between bulk qubits. In fact, you can detect the existence of these ghost qubits by computing the mutual information between each bulk qubit and everything else in the network. So both the boundary and other bulk qubits. And what you see is that you can still tune the brane this way, but you cannot tune it to be to come very deep into the bulk. You can just tune it a little bit away from extremality. On this top line, there is this bulk-inclusive mutual information, and this is the same that we had before. So if you minimize the bulk-inclusive one, you just obtain a near critical tension brane. If you minimize instead the one that we saw before, it looks like you're erasing the bulk, but actually all these bulk qubits still have entanglement with other bulk qubits. Mm-hmm.
Teleportation, and you know those are in the bulk are the modes that are very close. The vacuum modes are very close to the RT surface, roughly speaking. Right, and those are the ones that you're teleporting by design. Right? And you could just go and teleport the modes that correspond to the bulk particles as well, and see if you don't find them by that scheme. Right? Because I think your scheme is designed to teleport the modes that correspond to being near the RT surface.
I see, but it's still true that in this tensor network story, you really have some qubits that seem to not be reconstructible from the complementary region, but at the same time, they're still entangled with other bulk qubits. And that's something that in holography, it doesn't really make a lot of sense, at least to me. Like, we have a picture where this bulk first, this map becomes non-isometric, because you have the bulk to boundary map, because you have a whole bunch of states in the bulk, and you cannot represent them all on the boundary because, for example, say this specific state of the bulk qubits have a lot of zero modes. Like all these bulk qubits cannot be represented on the boundary, but nonetheless they're there and they are not disentangled from the rest of the bulk.
Sorry, when you say that there's the way that you measure whether something has been mapped to AC, right, is by this blue versus yellow scale?
It's computing the mutual information between each bulk qubit and all of the qubits in AC.
And where are the ghost qubits here?
The ghost qubit is by comparing the bottom to top. This is the same measurement basis. This is the mutual information between each bulk qubits and everything else, so AC plus other bulk qubits. So this tells you that if you just compute mutual information between, say, this qubit and AC, that's 0. But the mutual information between the same bulk qubit and AC plus the bulk is not 0.
But there are some qubits that are closer to the boundary, the yellow ones at the bottom.
These are fine. Yeah. So this is a circuit to see more or less what's going on. So you have measured region on the boundary, unmeasured region on the boundary. You have bulk qubits entangled with AC. But then you have some bulk qubits that are encoded both with AC and with bulk qubit. This bulk qubit 3 is only encoded with other bulk qubits, but not with the boundary. And then some of them are completely erased, which are these ones, essentially.
Yeah.
So it's a little bit more tricky in this setup, and we expect this to be a finite N effect. And so in order to fix this, we studied a stack of Maybe
I don't understand this picture. Why does it not have like one hexagon, one color? How can there be color gradients within a hexagon?
Yeah, no, this is an artifact of how this plot was made. You should imagine a rigid line here. Now, if you see each qubit is either yellow or blue, it's not. Well, you can have mutual information which is not, that's another problem, another finite N effect. You can have mutual information which is neither 0 nor 2. It's like some intermediate value between the bulk qubits and the boundary, because they have entanglement with both the boundary and other bulk qubits. So if you only compute the mutual information between, say, this bulk qubit and the boundary, maybe it's not 0, maybe it's 0.3, because then it's also entangled with other bulk qubits. It's a little like these are all finite N effects that go away when you consider a stack of epicodes.
Do the number of boundaries and bulk lengths in these diagrams represent the true number that you have?
Yes. Yeah, 21 to 55, if I remember well. I might be wrong about that.
If you take the ratio of the number of bulk lengths and boundary to infinity, then of course it will disappear.
If you take the ratio of bulk to boundary to be 0, this goes away. Yeah.
That's what you meant by finite N.
No, in this case, it's like an order 1 number. And so it's finite N. But what I mean by large N, I mean you have many more boundary legs than you have bulk legs.
Yeah, N to the 0 and N to the 1.
Essentially, yes. And so there is a way you can do this, which is considering a stack of happy codes. So you consider multiple copies of the happy code, and then you combine. So you have, say, m copies, and you have m set of bulk legs. So take this m set of bulk legs and build a single set of bulk legs out of it by combining the bulk legs using random unitaries. So in this way, what we're doing is that you increase by a factor of m the boundary legs without touching the number of bulk legs. And in this way, you're suppressing the rate of this code by 1 over m. So if you want the large n limit on the boundary, this is corresponding to having a large m limit where you have many stacks. So we studied this setup as well. We consider m equals 6, which is still numerically doable. And we saw that, in fact, these ghost qubits disappear. So if you erase them, meaning that you have 0 mutual information between bulk and boundary, you also have 0 mutual information between bulk and everything else, so boundary plus other bulk qubits. And this works well. And what we find is that, in general, the tensions are large. So you're actually always or mostly teleporting all of the bulk when you perform a measurement. This is a plot for this m equals 6 case. So you measure a large region, you always are teleporting almost all of these bulk qubits into the complementary region. You can tune a little bit away from criticality and trying to keep a little bit more qubits, but that's pretty hard to do. It's actually an open question whether we can obtain, say, 0 tension in these cases. I have some comment to do about it offline if anyone is interested, but for the bases that we looked at, and we definitely didn't look at all of them because there are many, for the measurement bases that we looked at, you cannot really tune the tension to be much lower than criticality. There might be some specific bases where this works, but it's not clear. So let me mention there is an upper bound for this teleportation, of course, which is what Rafael was talking about before. Essentially, you can only teleport information if you have enough entanglement resource to do it. So there's a corollary on the paper proved, which is tells you that the mutual information between the remaining region and the bulk qubits after measurement is bounded by the bulk entanglement entropy, the minimum between the bulk entanglement entropy and the entanglement entropy of region AC. Now, in semi-Gaussian holography, this is what I was talking about before. This SAC is just scaling as n squared, but you only have a finite, like an n to the 0 number of bulk degrees of freedom to teleport, and so you can always teleport as much as you want. Clearly, this is not true in tensor networks because you have a finite, you don't have a parametrically larger number of boundary legs with respect to the bulk legs. Another interesting, yeah. Mm-hmm.
You know, it's over well,
yeah.
But this inequality, should that be a max instead of?
No, it's. Should it be a max?
You're worried that SFB doesn't scale with n.
Yeah.
Yeah, but it means that the mutual it means that the mutual information, like if this term is large, then what you can teleport is essentially bounded by the information that you have in the bulk. While if this SOEC is smaller than this, it means that you cannot teleport all this information because you are limited by the amount of entanglement resource. Mm-hmm. Okay, so this is a lemma proved in the paper, but there is a corollary also, which is interesting, that in random tensor networks, this bound is saturated, meaning that if you have enough entanglement resource to teleport, you always teleport everything. So in random tensor network, there are only critical tension branes. And we actually also observed this. This was a lemma proven before, and then we observed in random tensor network, actually this happens. So this is my last slide. Just a quick recap of what's going on in random tensor networks, which is a very, very interesting part of the paper. Unfortunately, I didn't have time to go through. So if you have a random tensor network, this is built out of hard random tensors, and each leg in the network has a bond dimension, which is a very useful feature for holography because you can essentially tune towards the larger limit of semi-classical holography by taking the boundary bond dimension, D, to be much larger than the bulk bond dimension, BD. Now, we saw in this random tensor network analysis that the tension is always critical, so you always teleport all of the bulk when you perform a measurement. And in particular, there is a nice feature, which is if the measure region A is large, but it's not too large, and by this I mean that it's not too large in the sense that you still have entanglement resource to teleport the bulk, but it's large enough. In that case, the bulk is teleported, but the post-measurement bulk to boundary map is non-isometric. So this means that you are teleporting all the information into region AC, but if you want to reconstruct that information, you must perform some kind of state-dependent reconstruction. And this is like shown very nicely in the tensor network analysis. And interesting fact, the same analysis tells you that in the larger limit, so when you take the bond dimension of the boundary to be much larger than the bulk bond dimension, the map remains always isometric, meaning that in holography, like in our cases, you can expect to always be always have an isometric map. Okay, so this is just a quick recap. We saw that this local projective measurement on the boundary allow you to teleport the bulk information from the region that you measure to a complementary region. And in holography, we saw that boundary measurements corresponds to having a bulk end of the brains, and you can tune how much bulk information you teleport by changing the size of the region or changing the tension of the brain. And if you have these two disconnected regions, there is also an entanglement phase transition on the boundary induced by this measurement, which corresponds to connected, disconnected bulk transition. In tensor network, we saw that we have the amount of bulk teleported controlled by the size of region A and the measurement basis that you use. And most of the bulk is teleported always, or at least in all the cases that we were able to study, unless A is too large and then you don't have enough entanglement resource to make the teleportation. And in random tensor network, in particular, if this region A is large but not too large, then the post-measurement bulk to boundary map is non-isometric. I'll mention just a few open questions. One is, we discussed already this, so what is the correct way to physically regularize this ADS3 CFT to set up, splitting the slit or making them of finite height, and so on. Another interesting question which we also discussed is, suppose that you measure the CFT, how do you really measure on some Cardi state? So how do you operatively do that? That is not very clear. And another interesting question is this question that I mentioned about how brain tensions, lower brain tensions can be obtained in tensor networks. And so essentially, if you can project using a local projective measurement on the boundary on a product state of both the boundary and the bulk degrees of freedom, which is something a little bit tricky to do. Some future directions are applications of these to thermophile double states and SYK, and this is something we've been working on. Description of different measurements is also an interesting question. For example, this is a very, very local measurement and allows you to use this ADS BCFT prescription. But what if my measurement is some correlated or like maybe a little bit correlated or very correlated measurement? It's not very clear how to describe that holographically. It's probably not some end of the brain. It would be something else. It would be nice to see. So we saw that if you perform this measurement, you predict for the boundary theory disentangling, for example, disentangling phase transition. So it would be nice to see if this can be actually checked maybe on quantum computers, like trying to perform this experiment and see if the holographic description that we have predicts this. And it would be like, in some sense, a nice test for holography, I would say. And finally, we hope that this could also be a first step to describe measurement-induced phase transitions, which are transitions that you observe in quantum many-body systems, where if you perform measurement at some given rate, if the rate is large enough, you trigger entangling, disentangling phase transition. And in order to do that in our setup, you would need to have a measurement and then time evolution, Lorentzian time evolution, and then another measurement, and so try to study holographically this MIPT would be also a very nice thing to do. So this is all I have. Thank you.
Back to the H versus T plot when you were doing
Mm-hmm.
the
yeah.
Sorry, I gotta click a lot to
Sorry about that. Be the previous one? Yeah.
there we go. Okay. So I'm kind of, I guess this is always something about the ADS, the like pure gravity ADS BCFT thing that's always kind of bugged me. But so when you tune to positive tensions, of course everything is kind of nice. But when you're at negative tension, isn't it the case that you don't necessarily have that disconnected BTZ phase for certain negative tension? Because isn't it the case that if you have
Yep.
certain negative tensions that will intersect and you can't actually
Yeah.
draw the saddle?
Actually, that's an interesting question because you before talked about these intersecting saddles that you worked on. While we were working on this, at some point, while doing this calculation, I was like, oh, well, if you actually take negative tensions that are too large, or in general, also positive tension, brains could intersect. And so what's the deal with that? And I was about to actually start an analysis of what's going on there, but then we figured that it wasn't that relevant for our paper, and so we didn't study it. And I'm glad I didn't, because you would have schooled me. But the idea is that, yes, in principle, if you have large negative tension in the BTZ phase, those will definitely intersect. Now, what we do in this paper, since also first negative tensions here are not very relevant for what we're doing because we're interested in large positive to 0, essentially. There is this puzzle and also other puzzles of what's going on with negative tensions. For example, so we just limited to having negative tensions. We have a bound. If you look at the paper, there is a bound where we limit to negative tensions larger than some critical value, which is where the intersection happens. So we'll just don't study this final region right here.
But it's a function of how big the region you're measuring is, right? Because like when you do the mapping from the cylinder with 2 slits to
it's a function.
cylinder,
It's a function of the size, yeah.
Right, but then if you just have negative tension, then isn't there always going to be some region of measurement where if you take it to be too big, then you just can't really do this?
Yeah, that's right. The idea is that we don't need negative tensions in all this story. Yeah. So I could have just cut this plot here and just study positive tensions. Yeah. If you want to look at negative tensions, we have this bound, and this bound is dependent on the chosen size of the region that you measure. That's right.
And I guess in your tensor network models, you don't see any negative tension.
No, and that's an interesting point. Like negative tensions are a little tricky to understand for me because first, yes, in tensor network, we didn't observe any negative tension. And I'm wondering how physical it is projecting a negative boundary entropy boundary states. That it's not clear that it is for me because in tensor network, we don't see it. Also, if you think carefully about what's going on and you consider negative tensions, what you're doing is really projecting on a region and then affecting very much the entanglement wedge of the complementary region by pushing a brane farther, which is something which is not very clear if it's physical to me. I'm not saying, maybe I'm not understanding this, but the negative tension case is not really clear to us.
Are you actually like teleporting information into the post-measurement?
It seems, but there is no post-measurement wedge. So it's a little bit tricky. But for all this story, we care basically only about positive or zero tension, so it's not a big deal.
Is there some reason why you didn't study one interval?
Well, one interval was studied by Takayanagi, actually.
So this particular thing was, I mean...
a thing very similar to this one was studied by Takayanagi for a single interval. And he studied, and that's actually much simpler. This Boole teleportation is known because you just map one slit. Seeing that with one slit, you can map it to the upper half plane, and then it's much easier to do.
I didn't get from Takanaga's paper, which had a lot of beautiful things in it. I mean, the statement, for example, right, is that if you perform an appropriate measurement on half of the boundary, then the entire previous bulk is still there, basically. It's just encoded in the other half. I mean, the fact that you could, so of course there were limits of Takanaga's construction, which became a description of an arbitrarily large part of the remaining bulk. But you seem to be identifying precisely what kind of measurements I have to perform to actually teleport all the information over and which I shouldn't perform. So it's a non-trivial statement.
Yeah, I think.
Well, I don't think that was in the literature.
No, I don't think so. The difference is that in Takayanagi paper about this measurement story, he considers only one slit and zero tension because the questions he asks are very different. So he just assumes that there is zero tension and then just builds this map in the same way, except if you have a slit, well, he doesn't have a cylinder, he has like a CFT on a line, and this map leads you essentially, it's a different map that leads you to the upper half plane, and then just assumes that the tension is zero for simplicity. So not making any statement about what's the post-measurement state is, and how that affects the Boole dual. While in this case, the reason why you consider two is because if you consider a single slit and then you try to consider a post-measurement state with different boundary entropies and so different tensions of the brane, it's still not that clear. It's not as sharp of a question where the Boole teleportation is happening. It definitely is, but the problem is that not having a direct Boole dual of this situation, it's a little bit hard to determine whether the brane is sitting on the RT surface or not. But if you have this two-slit case, you have a very sharp way of asking the question, which is just about the connectivity of the post-measurement slice. Like if you're measuring a large region and the post-measurement slice is connected, then clearly bulk teleportation is happening, right?
You care about the topology.
What?
You care about the topology as a sort of.
We care about the connectivity of this slice, yeah. Because
But
in...
I think in the end that's not important, right? I mean,
No, I agree.
the way you were showing the result of the teleportation was, you're really emphasizing that you're getting close to the boundary.
But that's a cartoon, though.
Well, but I think it's the right cartoon.
I agree, but it's only a cartoon. I agree. I mean, I made a figure, so I agree. But it's a cartoon, but this is not super clear how to map exactly those brain trajectories back to this case because of all the singularities that we're talking about. So.
But it seems crucial that the way that you're latticizing the interval or intervals on which you're performing the measurement is in such a way that the number of lattice points sort of becomes dense near the edges.
Mm-hmm.
Right? I think that's what's allowing you to teleport the information about the
Why do you say it's important it's dense near the edges?
Well, I think that's where you have a lot of entanglement resources, first of all.
Right.
So, you don't gain much from teleporting like,
Mm-hmm.
a dense set of lattice points in the middle of the interval because they're not very entangled with the
Right. Yeah.
the
Okay.
outside. And also they don't encode the vacuum entanglement in the RT surface in the bulk, which is like the leading order thing that you
Mm-hmm.
need to stand over. That's where most of the entanglement is in most situations.
Right. Yeah.
So that, yeah.
But yeah, I agree with you that if you just consider one slit, and you need to in order to really see that teleportation is happening, you need to make the appropriate regularization and study the dual, and then you'll see that the brain is actually inside the entanglement wedge of the region you're measuring. But it's a little bit more complicated to show with a single region. With two regions, it's very easy because as long as this post-measurement line is connected, clearly the center was in the entanglement wedge of A before, and it's in the entanglement wedge of AC after. So that is very clear that it's happening. Just a sharp way to ask the question. But yeah, I agree that if you do it with one slit, it will be
When you have
also
these
good.
happy stacks,
Mm-hmm.
you should be able to see it there.
Oh yeah. In the HEP stacks, we did see it. I was talking about this bool calculation, but if you look at the HEP code, then definitely you see that. Like here, this is a single measure region, and clearly the RT surface will be something like this, and you just see that, yeah. In the tensor network story, it's much more evident.
More questions? If not, let's thank Stefano again.
Thank you.